So the question now, of course, is how can we do that computation in n times m, in O of n times m? Well, we'll see that we can somehow represent all those different recursive calls, these m times n recursive calls, by some matrix. Yeah, and the matrix is very simple. The columns basically represent the individual values of the sequence of the first sequence, and the rows represent the values of the second sequence. Yeah? And then we can just somehow align these two sequences, and we can, so to say, move forward from the lower right part, which is the end of both sequences, and just do the recursive steps, so to say, backwards. Yeah, and fill all these entries of this matrix. And it's even better because we can do that actually from left top to bottom. We can do that in many different ways actually, and we'll see how that works actually. And since the matrix has the size n times m, we only have to do n times m comparisons or computations, and then we are actually done with this efficient computation in O of n times m times, so to say. And we'll have a look at how that actually works. So first of all, this computation, this dynamic programming calculation scheme follows or somehow models this recursive step. Yeah, so we move actually from so if we consider this matrix where the rows and the columns are the corresponding values of the corresponding sequences, we'll see that right in a minute. We work from the tails, from the ends of both sequences. So we are somewhere in the matrix at position ij, and horizontal step, this one here, for example, this represents a deletion of the current character qi in q. Yeah, so I is the index running through q, and j is the index running through s in that case. Yeah? So a horizontal step obviously represents a deletion in q, because we move forward to the start of q in this direction. The other way around, the vertical step is an insertion of a character, of the corresponding character j in q at position I. Yeah, so in that case we remain at q and move forward to the start of s in that case, one character or one position. Yeah, and a diagonal step, this one here, represents either substitution if those two things are different, or a match if these two things are actually equivalent or equal. Yeah? So those are the four cases that we can have. The three cases if the last elements of both the actual last elements of both q and s are not equal, and the fourth case is if they are equal, then we have this one here. Yeah, of course. So those are the four different cases here, and a match is the same as a substitute. The only difference is that we calculate one edit operation in the later case, and in the first case, of course, not. But we move in both cases. We move just one step towards the start in both sequences, and with the insert we move only with s, and with the delete we move only with in q. Yeah, and we can see that here with these different steps here: horizontal, vertical, and diagonal step. Sorry, horizontal, of course, this way, vertical this way, and diagonal. So this is the visualization of the dynamic programming scheme here. So we start, for example, with the two full sequences, Rhabarber and Barbarei here, and so a vertical step would be an insertion of this character which is the current position, the last position of S in that case. Yeah, a horizontal move would be a deletion of the last character here of Q, and the diagonal step would be a substitution in that case, because R and I are not equal to each other. So in that case, this would be a substitution. Yeah. So if so, for example, here the last thing that we consider here is are equal elements here, E and E, then in this case this would be not a substitution but a match actually. Yeah. So we also call that a substitution, E by E, but in that case, of course, that would not cost some operation because it's a match in that case. Yeah. And we can move from bottom right, so to say, in this matrix up to top left. And the nice thing with the dynamic programming scheme is that we can somehow reverse this process, and we'll see that. So all possible solutions, first of all, so the edit distance on all subsequences between Q and S can be stored in that n times m matrix, which we call D here, following exactly this scheme here. So we can model all these different alignments here, as you can already see in a matrix. Yeah? And basically we can compute these entries of this matrix here, or of this matrix here actually, by somehow performing the programming scheme that we just saw here, in a kind of reverse order. Yeah? So we can compute actually ij by based on this value or this value or this value. Of course, we can do that because that is a recursive thing. So if we start with the base cases, which are one of the two things are 0, then we can, of course, compute the next iteration of the recursion and the next iteration of the recursion based on that, and so on and so on and so on. Yeah? So we can, of course, in order to compute the final alignment between I and J, or the edit distance between I and J, or at position I and J, of course, that relies on these predecessors in the recursion. And if we start with the base cases, then we can, of course, one step by the next, compute the final result. Yeah. So, and we can do that just by doing exactly what I said. Yeah. So we start with the base cases. Well, those are the base cases basically, but we start, or we have actually an n+1 times m+1 matrix, because we start the index with 0. 0 means that we have empty sequences. Yeah. And we say, of course, matching two empty sequences will give you a 0. Now, for the rows and the columns, we can easily set the values, because well, look at this one here, maybe in this example here. So we have the sequence Tor and the sequence Tier, yeah, and this is basically the zero position. So we start with the sequences with position 1, yeah. So we start here with the empty positions, and of course at the empty positions we have 0. Now for the rows, it's clear that if we want to match this 0 sequence, yeah, to just T, we have to spend one operation. If we match the 0 sequence to To, we have to do 2 operations. We have to do 2 inserts or 2 deletes, whatever, which way around, it's not important. Yeah, and the same holds true with the sequence Tor. We need 3 operations, obviously. Yeah, so it's very easy to set up the values here for the first row and also for the first column accordingly, because if we want to match this the empty sequence to T, we need 1 operation. To Ti, we need 2 operations. To Tie, we need 3, and so on and so on and so on. Yeah? So we see here the left upper entry is 0, of course, and for the first row and for the first column, we just set it to the number of the corresponding color, or the number of the corresponding row, yeah? Because that's very easy. So it's very easy to set up the first row and the first column, And now we can even compute the next parts. Yeah. So for example, the entry EJ is basically the minimum of what? Well, we have to look at, well, if we look at the programming scheme, we have to look at the left predecessor, the upper predecessor, and the diagonal predecessor. Yeah? So if we want to compute this guy here, obviously we have to look at this one, and this one here. Yeah. And now, depending on whatever it is, well, we have to look at the values. Well, t here, upper T here, and uppercase T here. So it's a match in that case. Yeah. So the new value depends on the diagonal value plus 0, meaning that we don't have that's a match. We don't have to do anything. Yeah. So we move from here to here. So it's the minimum of all that stuff here. Yeah. And then we can do the same with this one here, where we have to look at this one here, and this one here. And in that case, okay, we want to match T and O. In that case, we can do that by simply in that case that's an insertion. Yeah, so we are in this case here. So we have +1 from the horizontal neighbor. Yeah, and so on and so on and so on. So we can easily compute the new value based on, depending on what it is, a substitution, a match, an insertion, or a deletion, easily compute any value in between here from the predecessor somehow, yeah, meaning the upper predecessor, the left predecessor, or the diagonal predecessor, so to say. Yeah. Yeah, and if you do that starting from down here, yeah, so that is again the thing that I wanted to show you. So that is the definition. And now if you do that, like in this example here, the entry on the lower right part displays the value of the added distance between the two sequences in that case. Yeah.